Hello there and welcome back to this video series on control systems. Over the past few videos we have been looking at transient response specifications, then steady state error constants, and then in specific in past couple of videos we started looking at what we mean by BIBO stability, bounded input, bounded output stability, and also looked at conditions for BIBO stability. After watching this video, perhaps you will be able to apply Routh criterion to check for BIBO stability. With that brief prelude, let us go into the video itself and see what is Routh criterion. Okay. We know that characteristic equation, which is the denominator of closed loop transfer function equal to 0, is given in this order. If it's an nth order system, you have an nth order polynomial in S with constant coefficients. And if any root of this equation has positive real part, then we said it's unstable. Okay. For that we need to know what are the roots of this. Okay. And see how many roots have positive real part. Even if one root has positive real part, then system is definitely unstable. Routh's criterion enables us to find how many roots of the characteristic equation have positive real part without solving it. Okay, that's the beauty of it. You don't have to solve this equation, but you can say something about how many roots of characteristic equation have positive real part. So given this characteristic equation, we build a Routh's array. This is an array, first two rows of which are built from the coefficients of the characteristic equation itself. Let me play back a little bit and show you what I mean by it. First two rows are built from the characteristic equation terms. We call it S power n row. You can see that the coefficients of an minus 2, an minus 4, and so on are taken from the characteristic equation and put into one row. We call that as row corresponding to S power n. See an minus 2, an minus 4, and so on, then a2 and a0. That is first row, which corresponds to S power n. Then the second row corresponds to S power n minus 1. You can see an minus 1, an minus 3, an minus 5, and so on, a3 and a1. These are the first two rows. Subsequent rows are built from these first two rows. Let us see how it is done. Okay, S power n minus 2 row is built from the previous two rows. That is, you can see you are multiplying cross up, then cross left up, cross up right with a positive sign, cross up left with a negative sign. An minus 1, an minus 2, product of them minus the product of these two. This an minus 1 is called the pivot element. That pivot element appears in the denominator formula for all these elements for C1, and then let us look at C2. See an minus 1, an minus 4, an minus 5, an divided by an minus 1. That is the reason why this an minus 1 is called the pivot element. We perform the same operations. Each row is built from the previous two rows using the same formula: cross up positive, cross up right positive, cross up left negative, divided by the pivot element. Let us look at this a little bit and see what it means to us. You will see for sign changes, is an positive, an minus 1 positive, and so on. If it is positive and this is negative, you call it as a sign change. If this is negative and this is positive, you count it as another sign change. The number of sign changes in this column indicate the number of roots with positive real part. We'll try to see this Routh's array once again in a kind of clear way. First row is built from coefficients. Quotient of n, s to the power of n, quotient of s to the power of n minus 2, and so on. So each column is differing from next column by a power of 2. Sn, Sn minus 2, and so on. Similarly, the next row is built by n minus 1, s for n minus 3, and so on up to a3, a1. The subsequent row, the c1, c2, c3 are computed from previous two rows. This an minus 1 is the pivot. Then the formula is simple: cross up right product minus cross left up product divided by pivot element. Similarly, you find d1 and d2. You can see c1 an minus 3 minus c2 an minus 1 divided by c1. So this an minus 1, c1, d1, they are all pivot elements. Once you build this array, look for number of sign changes. If there are any sign changes, that would mean there are roots with positive real part, and thus the system is stable. So if the system has to be stable, the number of sign changes must be 0 in that column. We'll look at a couple of examples of applying this Routh's criterion. Okay, it's a fourth order polynomial. So you have one row corresponding to s power 4, one for s cube, one for s square, one for s, and one for constant term, that is s power 0. S power 4 row consists of 1, this quotient is 35, this is 24. Similarly, this s cube row consists of two elements, 10 and 50. Because there is nothing else after 24, we put a 0 to remind us that there is nothing else there. Then this s square row, 10 multiplied by 35 minus 50 divided by 10. 350 minus 50, 300 by 10 is 30. That 30 comes here. Then you have 10 multiplied by 24 minus 0 multiplied by 1 divided by 10. That is 24 comes over there. Similarly, we'll build the next row. 30 multiplied by 50 minus 24 multiplied by 10 divided by 30. So you got 42 here. 30 into 0 minus 0 into 10 divided by 30. You got 0 here. Carefully notice, in finding this 30 and 24, 10 is the pivot element. Okay. Similarly, in finding this 42 and 0, 30 will be the pivot element. We'll compute the final row. 42 multiplied by 24 minus 0 multiplied by 30 whole divided by 42, that is 24. This is positive, this is positive, this is positive, this is positive, and this is positive. There is no sign change in this column. So there is no root which has positive real part. So the system is stable. In fact, if you solve for the root, you see that minus 1, minus 2, minus 3, minus 4 are the roots. Because all of them have negative real part, the system is stable. Let us look at another example. Another example, again it's a fourth order system. One quick thumb rule you can see, if there is a sign change in the coefficients of this polynomial, definitely at least one root is there on the right hand side of imaginary axis, or one root with positive real part. However, we build Routh's array to see the intricacies. Let us see, we will see one important aspect of it. Okay, first row is written, then next row is 5 minus 5, 0, and look at the s square row, 6, and then minus 6. 5 into 5, 30, 30 plus 5, 30 plus 6, 36 divided by 5 is, you get 6 here. 25 plus 5, 30, 30 divided by 5 is 6. Similarly, 5 into minus 6 minus 0 into 1 is minus 6. Look at the third row. Something surprising happened. This pivot element became 0. For computing the next row, we use the pivot row as the first element in the pivot row as the denominator. See here 5. This 5 comes in the denominator here, denominator here. 6 comes in the denominator. 0 cannot come in the denominator. So we'll do a little mathematical trick, that is, we replace that 0 by a small quantity, positive quantity, epsilon, and go ahead with computation. If you put small epsilon here, epsilon into minus 6, minus 0 into minus 6 by epsilon is minus 6. So this is positive, 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 and there is a negative. So there is one sign change. So there is one root with positive real part, and hence the system is unstable. And in fact, if you solve for all the roots, you see that one root is plus 1. Others are minus 3, minus 1, and minus 2. Even if one root has positive real part, the system is no longer stable. So in summary, we see that Routh's array is a very simple to use technique to determine the BIBO stability of the system, and it does that without actually solving for the roots of the characteristic equation, which is a very beautiful thing. That is, you're trying to say something about the solution without solving the problem. That's one nice feature that runs through many topics in control systems. And I think that's all we have for now. Have a great day.